Hi, in this video tutorial, I'm going to focus on explainable geospatial machine learning for modeling forest canopy height. So why do we need explainable machine learning models? Okay, so most of the advanced machine learning models that we use are very good at making accurate predictions. However, they are very difficult to interpret. So let's take a look at this graph that we have. As you can see, most of these deep learning models and machine learning models such as support vector machines and random forest, they've got a very high accuracy, but the interpretability is quite low. This is because most of these advanced models are considered black box. That is, they offer little insights into how the predictions are made. For example, it will be difficult to tell which predictors influence the model outcome. Therefore, there's a massive need for explainable machine learning methods so that we can gain insights into the model outcome. So this is quite important for the stakeholders also to understand how the model work. Right, so in this lab tutorial, we are going to use explainable machine learning for modeling forest canopy height. So we are going to use the GEDI level 2 canopy height data, Sentinel-2 imagery, and two spectral indices, that is the Canopy, chlorophyll content index, and the normalized different vegetation index. We are going to use a random forest method as our choice of the machine learning method. Right, so first we need to install the libraries that we're going to use in this code. Please take note, I've already prepared the code beforehand, and I've run some of the modules because to run some of the code parts, they take time to run. So I'm just going to do the explanation, and then you can run the code on your own. So the first stage is to install the libraries such as the Rasterio and EarthPy. So Rasterio is good for reading the raster data, for example, satellite imagery or aerial imagery. And EarthPy is used for data processing or plotting or visualizing the spatial data sets. So once you run, install, the code is going to download the Rasterio and EarthPy libraries. So after that, we are going to import the libraries that we are going to use in this code. So we import the Rasterio and the EarthPy that we have installed. And then we're also going to install other libraries that are within the Collab environment. So libraries such as GeoPandas, NumPy, Seaborn, Matplotlib, and then the scikit libraries that we are going to use for our machine learning modeling. Right, after that, after running this, we come to setting up our Collab environment. So first of all, we are going to make sure that we understand what we are going to do here. Right, first, I've prepared the training data set that we are going to use for this lab. So the training data set is in my Google Drive. So for your case, You can also prepare the same training dataset using the code that I'm going to leave in the description below. So this is a JavaScript code which shows you how you prepare the training dataset in Google Earth Engine. So you can adapt the same code in order to create training dataset for your study area or project area. So once you create that training dataset, you can export the datasets to your Google Drive. And then after that, here you just run this line of code, and then you are going to be asked for your password so that the code can have access to your Google Drive. Once you grant that access to your Google Drive, next we are going to access the dataset that we are going to use in this collab environment. So we are going to set the path where you have the training dataset. So my training dataset, which is basically a data frame containing the predictor variables and the response variable, is here in this path. Okay, so it's saved in .csv. And I also have the path to where my composite images that contains the Sentinel-2 imagery and the two spectral indices. So I need that imagery later when we run the prediction in order to produce the forest canopy height map. Right, we are going to define here the predictors, okay, so that we tell the code what our predictors are. So in this case, our predictors we have Sentinel-2 bands and the two spectral indices derived from Sentinel from the Sentinel-2 imagery. Right, so we have band 3, which is green. We have band 4, red. Band 5, which is the vegetation red edge 1, and then we have band 6, which is vegetation red edge 2, and then we have band 7, which is the vegetation red 3. We also have band 8 here, which is near infrared. Band 11, which is the shortwave infrared 1, and band 12, which is the shortwave infrared 2. Then we have our two indices that I've mentioned before, CCCI here and the NDVI. Right, for our response variable, we have the GEDI level 2 canopy height. So here it is defined as RH, which just stands for relative height 98. So this represents the 98th percentile of the GEDI LiDAR wave, which is up to the 98%. Okay, so this is the one that we are going to use, RH98. Okay, and then following that, we are going to load the Sentinel-2 imagery and display it so that we see how it looks. So this is the code for loading the image using the rasterio library. Okay, so this is our image. So please take note. It has got here 10 bands. So we have our Sentinel-2 bands plus the spectral indices that I've added in this composite. And the image dimension here, the image dimension. So we have 1,814 multiplied by 4,442. Right, so this is our dimension for our image. Okay, next we are going to prepare the datasets for modeling. So we are going to load in the CSV file that contains the training dataset. Okay, so we're just simply going to read it, and we are going to define the predictors, that is the predictor variables and the response variable. And then here we display, we have our Sentinel-2 bands plus the spectral indices. These are the predictors, and then our RH98. So this is the GEDI level 2 forest canopy height response variable. Right, so to set up for training, we need to split the training data into training set and then the test set. So here we are going to use the train test split from the scikit-learn library. Okay, so we are going to have 20% data which is going to be used for training, and then 20% which you are going to use for testing. So you can just write this line of code. Okay, we are also going to print so that we can check the features. Right, as you can see here, we have for the training data set, we have 492 predictors. Okay, 492 predictors. That means we have 10 predictors. The 8 Sentinel-2 bands plus 2 spectral indices. And for the test features, we have 123 points with 10 features. So again, 10 predictors, the 8 Sentinel-2 bands, and the 2 spectral indices. And for our response variable, we have one response variable, which is the GEDI level 2A forest canopy height. Okay, so we have also 492 points, and for the test we have 123 points for our response variable. Right, next we want to check if our dataset contains missing values, because most of the machine learning models, such as the random forest, they do not handle missing values very well. So if we run this code, we see that we don't have any problem with the missing values. Okay, so that's good. And the next, we want to perform exploratory data analysis. So this is important to understand the distribution of our data before we build a machine learning model. So first thing we'll do is we will create a data frame. Okay, and we are going to specifically point to our forest canopy height data. This is the, remember, this is before we are calling it the RH98, so I have changed it to FCH, which is just the forest canopy height. So we are going to specify our predictor variables plus the response variable. Right, and then we are going to check our data set to see if everything's okay, and then everything's fine. We have our Sentinel-2 bands here, plus our spectral indices and our response variable, which is the GEDI forest canopy height. Right, next we are going to check the structure of our data set, and then we see that here we have 492 entries. Okay, and then these are our columns which we have just seen. We have our Sentinel-2 bands, the spectral indices, and our response variable, which is the canopy height. But next we want to use the describe method in order to get the summary statistics of the training data set. So if we run this line of code, we get our summary statistics, but this is quite difficult to understand. So let's go and plot graphs that we can easily interpret. So we are going to create the box and density plot. So we will start with the response variable, which is the canopy height. So we are going to plot the box plot, and also we are going to create here the density plot showing canopy height. Okay, so if we run this code, we see that for the canopy height, it's actually ranging mostly between 7, between 7, let me just reduce the size here so that you can see. Okay. Right, maybe between around 7 and 15 meters. But we have a problem here with the outliers. We have many outliers above 25 meters. So this is quite a problem. Because from studies, previous studies in the study area, usually the tallest trees are between 7 and 15 meters. So here we have something over 25 meters. So this is some errors, some measurement errors from the GEDI sensor. Okay, we can also see the same distribution here, that we have mostly the peak between 7 and 15 meters for the canopy height. And then we also have the distribution going up to 35 meters, which is not good. Right, and next we generate plots for the predictor variables. For this case, we do it for the Sentinel-2 bands. So Sentinel-2 bands, these are the mean spectral reflectance from band 3 to band 12. We see here that we have the highest spectral reflectance for the band 8, which is near infrared, since this place is highly vegetated. And also the vegetation red edge bands also have got very relatively high mean spectral reflectance. And the two spectral indices here, they don't give the spectral reflectance as such. It is just a range of values between minus 1 and 1, especially for the NDVI. Right, next we check the box plots for all the predictor variables. And here we see the distribution of the values. Mostly all the predictor variables here have got showing outliers. Okay, so we have challenges with our data set. Please take note of this. This is going to influence the model. And the next, we plot the density and histogram. So this is the density plot. Again, it's just showing the distribution of the values. For example, for band 3, values range between 0.2 and 0.25 for the spectral reflectance. So very narrow spectral reflectance for these bands. For this band, sorry. But there's a change with other bands. We can see here the distribution. For example, for band 12, it's quite broad. It covers many ranges. Right, and next we are going to start we're going to start to train our model. Okay, so first we are going to set up the random forest model. We are going to define the random seed for reproducibility here, and I've just put the seed as 42. And here we define the random forest regressor, and then we fit our model. Okay, so we are putting the training data set, the predictors, which is X underbar train. So these are the predictors. Then Y underbar train is the response variable. So these are the 80% of the training data set that we are using to train the model. And then we are also going to check how the model is performing using the RMSE metric for the random forest regression model. And we also want to use the k-fold cross-validation in order to check how the models perform according to the different subsets that we've created. So here we have 10 subsets for checking the model performance. Right, if we run the code, we can also plot a graph showing how the model can the model is performing. Okay, so this code produces this graph which shows the model performance. And here we can see that the range is quite low, just between 5 and 6 meters for the RMSE. And the best models here are models 6 and 7, which have the lowest RMSE. But we can see that here the model performance is not quite good. The range is quite low, between 5 and 6. So it means there are some problems here. And then next, we also want to now to check the predicted canopy height and the reference GEDI canopy height. So here we are going to use to calculate metrics such as MBE, that is calculating the mean bias error, and then the RMSE and the R squared. And please take note here, first we need to do the prediction. We need to predict the model. So we are taking the model that we got from random forest, and then we are going to predict it using the data that we did not use, so the test data. So this is the data that the model does not see. So this is going to give us an idea of how the model is actually performing. Right? If we run this code, we are going to produce this scatter plot showing the reference versus the estimated canopy height. As we can see, the model actually is not doing a good job. Mean bias error, root mean square error, and the other square show that model performance is quite poor. And one of the reasons could be the presence of these outliers in the data set. So remember, we didn't do any data cleaning of the GEDI level 2 data set. So this is something that we will do in the other upcoming courses, so that we improve the accuracy of the model. Right, after that we will just predict and display the final forest canopy height. So here we are just going to take the original Sentinel-2 imagery, so the image input, okay, and then we are going to, remember we have 10 predictor variables. So Sentinel-2 bands, 8 Sentinel-2 bands, and plus 2 spectral indices. And then we are going to take that image, and then we combine it with the random forest model, and then we are going to do the prediction. So this is going to produce the forest canopy height map. So this is the map again. The legend here showing that forest height ranges between 7.5 meters to 25 meters. which is kind of too high for this study area. We would want to expect a forest height between 7 and 15 meters. So again, this is a problem with the model. So we now want to check why the model is performing like this. We need to understand the reason for that. Okay, so when you finish, you can, if you want, you can save the model, and then it is going to be saved in your Google Drive. You can download it from Google Drive and then display it in any GIS software. You can display it in QGIS or ArcGIS. Right. Okay, so this is the first part of just running the random forest model and preparing the forest canopy. Okay, so we come to the second part of our lab tutorial. So in this part, we are going to perform explainable machine learning. So there are many explainable machine learning methods. So in this lab tutorial, we are going to use the SHAP method. So this is the Shapley Additive Explanation. So this is one of the most popular machine learning method. So SHAP is based on Shapley values, which was introduced by Lloyd Shapley in 1953. So this is a concept which comes from the cooperative game theory. So it has been adapted for explaining the machine learning models. Okay, and here the idea is that the Shapley values just provide a way to quantify the contribution of each predictor variables to a prediction. So it does this by calculating the average marginal contribution across all the possible subsets of the predictions. So the Shapley value is actually good because it tries to distribute the values fairly, okay, among all the different predictor variables. So this gives us an idea of the contribution of each predictor variable in the model. Okay, so what are we going to do next? We first want to import the SHAP library. So the SHAP library is already installed in Colab, so we just want to import it. So first we're going to import it, and next we are going to create an explainer. Okay, so the explainer is going to contain the SHAP values. So that means it is going to take the random forest model that we have created and used previously, and then it combines that with the predictor variables, because remember, we want to check the impact of each predictor variable to the model. So these predictor variables, they are in the X and underbar train object here. So remember, we have the 10 predictor variables, that is the Sentinel-2 bands plus the 2 spectral indices. Right, so these SHAP values are going to be contained here in the SHAP values RF. Okay, this whole operation, this code takes about 5 minutes to run for my from my study area. Please take note, this depends on the size of your data set. So if you've got a huge data set, it is going to take more time. So maybe it would be better to use kind of a batch processing so that you can optimize the memory for running this code. Right, so after running this, we are going to just check the the type and attributes to see if everything is fine. So if we check here, we see that we have our this is the amount of the training data that we noticed earlier on, so 492, and the predictor variables which are 10. So everything is fine here. And then the first thing that we want to do is we want to plot the SHAP summary graph. In this case, we want to define the summary plot as a bar graph. So this is going to be like a bar graph. So if we run the code, we get our bar graph, and the bar graph is going to show the predictor variables that contributed to the model performance. So it's going to just to order them in order of feature importance. So here we can see that the CCI is the most contribution, and followed by NDVI. But as we can see, this summary plot bar graph is just showing the magnitude of the contribution, okay, in terms of the absolute values. It is not giving the direction of the contribution. It is not showing whether the predictor variable had a positive contribution or a negative contribution to the model. Okay, so to check that, we can create another summary plot. So now this is based on the dot graph. So this is now going to show us the actual contribution of each predictor variable, if it had a positive or a negative contribution. So here we can clearly see that the CCI has got more positive contribution, as seen by the these red dots, which shows a high contribution, and towards the positive side. Okay, if we look at the other predictor variables, we can see that the contribution is actually very low, maybe centered around 0, which means it's not giving. It's not actually providing much influence or impact to the model. Okay, so we will check later how this goes. Right, so after that, we can also create a simple dependence scatter plot to understand again how the each predictor variable is contributing to the model. So this is a one code that we can use. Simple. We are just here calling the SHAP values, and then we create a plot for each predictor variable. So now it's showing the impact of each predictor variable to the model. So if we look closely, band 3, band 4, band 5, and band 6 here, they are mostly centered around 0. Okay, so the predictions are just ranging between minus 0.5 and 0.5, and centered around 0. So the contribution is quite low. We have a slight change here in band 7 and band 8, but still contribution is quite low. Same for band 11 and band 12. We notice a marginal change, a very big change here in the CCI and NDVI. So here we can see that there's more of a positive contribution to the model outcome. So the other bands, actually performance is quite weak. Right, so this is just showing the impact of each predictor variables graphically, but we don't have a sense of where the most of the contributions are having the impact in the model. So we need now to create the SHAP maps. So SHAP maps they show the impact of each predictor variable spatially. Okay, so how it contributes to the model to the model outcome. So one, we can understand the contribution to the model outcome, and also we can understand where it has most impact in the study area. So this is quite important, because for us who are doing, we're using remote sensing data, or we're doing a geospatial analysis, we need to have this spatial perspective. Right, so one of the problems now is that computing the SHAP maps takes a lot of time. So if I use the whole study area, this is going to take about 20 hours to compute. So this is quite a lot. So what I've done is I've created a subset boundary for the study area. So this subset for the study area, I created this boundary in QGIS, and then I imported it here in Colab, so that I can run the computation of the SHAP maps for only the subset boundary. Okay, so what do we do? So the first step is to import the boundary, and then we are also going to load the original images, that is the predictors that we have, the Sentinel-2 bands plus the spectral indices. And then we are going to overlay the subset boundary on the imagery, and then we will clip the images, all the predictor variables, so that we have got a smaller area that we can analyze. So this is just the code to do this. Again, we import the predictor variables using rasterio, and then you use the boundary subset to do the clipping. Okay, and then next we just want to check the data sets, for example, the dimension of the new data sets that we have, and the total number of pixels. So please take a look. Now we have 808 and 1306 dimensions. These are the dimensions for our new imagery. So remember, when we started, I showed you the dimension of the original image. So we have actually reduced the image dimension so that we run this computation. So the next thing is we select the predictors that we want to prepare the SHAP maps for. So we all have these predictors, but if we run this again, it will take time. So for the purposes of this lab, I've just selected CCCI band 7, the vegetation red edge 3, and then the near infrared, and then NDVI. Right, so these are our selected features. So we are going to create our SHAP value explainer. Here I'm going to use the SHAP tree explainer, because this is a faster, at least to do the computation. And then I'm going to use batch processing here. Okay, so selecting about 10,000 pixels per batch. So this is just to optimize the system memory. Okay, so you can play around with this figure according to the size of your study area. Right, and then after that we determine our SHAP values for the subset and for each batch, and then we run the code to create the SHAP maps for each predictors. That is for the four predictors that we have created. And here we are just defining the color range for our map based on the minimum and maximum from our SHAP values. Then finally we just run this one. So this code takes about 3 hours to run. The creation of the SHAP maps takes 3 hours for the subset. I haven't found a way to reduce the time, to optimize the code. So I'll be playing around with this. If there's anyone with an idea of how we can improve this computation, your input is welcome. Right, then finally we just run this code to display the SHAP maps. So here is the result showing the SHAP maps. So for CCI, as you can see, it has got very high impact to the model. It contributes a lot, and we can also visually see visually that the predictions are quite good based on the CCI. And for band 7, we see very reduction in performance. So this is quite poor performance. We see areas where the model missed a lot. So that shows that band 7 is not doing a good job. It doesn't have much impact in the model. For band 8, it's better than band 7, but still the impact is not that much. We still have a lot of areas where it did not do a good job. And then finally we have NDVI. NDVI is much better than band 8, but less than the CCI. So again, this is quite important because it is giving us the visualization of the spatial variability of each predictor variable. So we can see where the model is doing good work, and we can work on improving the next model. So this is quite informative. So just in conclusion, so this is the subset area that I've created, and these are the predictor variables that I've just used for this lab tutorial. So please feel free to play around with the code and see where you can whether you can improve the creation of the SHAP maps. I think these SHAP maps are quite important. We just don't want the graphical representation, but we want actually the map representation since we are analyzing geospatial data. Right, so thank you very much for watching this video. Please access the additional materials that I've put in the description below, so that you can try to understand this model. The code also is available in GitHub, and also there's this free ebook that I prepared. It has all the explanation about the results from this code. So please also download the free ebook and then go through it and then try it with your own dataset.